So as we look at some applications of spanning trees, we are again going to see those weighted graphs that we saw with our Hamilton circuits. What we're usually trying to do in a context problem with a spanning tree is find what's called a minimal spanning tree. Just like with our Hamilton circuits, when we looked at weighted graphs, we were looking for that weighted graph with the shortest length. How could I travel along the edges with the smallest labels, the smallest weights? Same idea here, but this time for our spanning tree. So if we take a look at a small graph here, in this instance, if I ask you to find the minimal spanning tree, that's probably not that difficult. Even if I had to guess and check, I don't have that many options. I've got 3 vertices, so that means I'm only going to use 2 edges to connect them. So I could pick 4 and 7, I could pick 4 and 2, or I could pick 2 and 7. 4 and 7 would give me 11 as the total weight for my completed graph, or the length for that. We don't care about it being a path, but we talked about lengths for paths with our Hamilton circuits. I could have 6 or I could have 9. Obviously 6 is the smallest of our options here, so that would be my minimal spanning tree. Now, as our graphs get more complicated, this sort of guess and check option becomes more tedious. So instead of guessing and checking for every possible spanning tree I could have for my graph, what we're going to use instead is something called Kruskal's algorithm. So here's the big idea. For Kruskal's algorithm, it's going to work very similar to what we looked at for our minimal spanning trees. So we're going to start this time, since we don't care about traveling in a path, I don't care about starting in a vertex, we're going to pick an edge. So I'm going to start with the edge of least weight. Whatever that smallest label is in your graph, that's the first edge you want to include. And because an edge is between 2 vertices, by default you're going to get the vertex on either end of that edge. So start with the edge of least weight. If there's more than one, if there's a tie, if you've got 2 edges of 2 and that's your least weight in the graph, then your official directions are pick at random. Okay, so that means that you may get a different final result than your neighbor, and that's okay. And then to make your next selection out of the edges not yet chosen, again, pick the one of minimal weight, okay? Just making sure that you are not creating a path or a circuit. It's fine if it's a path. Again, it doesn't have to be. Make sure there are no circuits. You don't want any loops anywhere in your path. Make sure there are no circuits. Okay? And then I repeat this process. Out of the edges left over, whatever vertices I have left to connect, we keep choosing the edge of minimal weight as long as the subgraph doesn't form a circuit. And again, if you've got a tie, pick at random. You keep doing this until your graph, your spanning tree, has all the vertices and is connected. So let's take a look at an example of this. So here we have a weighted graph. I want to find a minimal spanning tree for this weighted graph. So I'm going to follow Kruskal's algorithm. I'm going to start by selecting the edge with the smallest weight. In this graph, that would be 1. So I'm going to include this edge in my graph. That means I have A and B included in my graph right now. Now I'm again going to look for the edge with the smallest weight. That's 2. So I'm going to include this edge. Okay. In this case, it just so happens to be connected to the portion of the graph I've already included. Doesn't have to be. Since I've included this edge, now I also get vertex D. My next smallest edge would be 3. So I include this edge. It doesn't make a circuit, so I'm okay. And then because I've included this, I get C and E. Now at this point, I have every vertex in the graph, but my spanning tree is not connected. I don't have a way to get from D to C. I can get from B to D. That's fine. I can get between E and C, but I can't get, again, from A to C or from B to E. So that means I need one more edge here. My next smallest edge in the graph is 4, It will connect these two pieces that I have, and it doesn't make a circuit. So 4 is the last edge in my spanning tree. Okay, and the complete weight for this spanning tree would be 1 plus 2 plus 3 plus 4. So our graph has a weight of 10. Since it's not a path, we don't really talk about lengths, but we can say that the weight of this spanning tree would be 10. So let's take a look at a couple more examples of this same idea. For example 5, it says a farmer wants to install an irrigation system for his farm, but his plots are divided into sections that aren't all necessarily right next to one another. And then we have our water source over here. So here's our like real life visual of our different sections of land and our water source. And then over here, we have this same thing. We've just taken this and sort of spread these points out so that we don't have these bent edges for our graph. And then we've also labeled the graph. So we have our weighted graph here. And these represent the different costs to put in irrigation systems between different plots of land or between different plots of land and the water source. So for example, to connect C directly to the water source would cost $81. It's not represented in our problem, but we'll say dollars. To connect the water source to plot A would be $49. If I want to connect B and C together, that would be $62. That's what all this represents here. So we want to figure out what's the cheapest option for this irrigation system. We want a minimal spanning tree. So I'm going to start the same way I did before. I'm going to look for the edge of least weight. What's the smallest number in here? The smallest number in here is 25. That's this edge right here. So that connects B and our water source. Okay. And I'm just going to jot that down here. And then we need to keep going. So B is connected to our water source. Great. But all of our plots need to be connected. Now, keep in mind, again, this is a minimal spanning tree. Not everything has to be directly connected to the water source. So, for example, if my next option were 62, that would mean I could run a line from the water I have going to B and direct that over to C as well. So that's why we're looking at a spanning tree here. So our next cheapest option for irrigation would be 38, and I've got two 38s here. Official directions are choose at random. So I'm going to pick this one just because I saw it first. No other special reason. That gets me A and C. And now I'm going to again choose the smallest number I have available to me. Well, that's the other 38. I can pick this one without making a circuit, so I'm going to choose that. At this point, I've included every vertex in my spanning tree, but they're not connected. So, for example, I have water going to B, but nowhere else because this portion of my graph is not connected to this portion of my graph. So I'm going to need one more edge here that doesn't make a circuit. So my next smallest weight would be this 42 right here. So the cost for my irrigation system would be the 25 plus 38 plus 38 plus 42. So that would give me a total of 143, and we'll just assume that that's dollars. Minimal spanning tree. We have one more example we're going to take a look at. For example 6, we're looking at some infrastructure here. We have 6 different towns that we want to be able to connect. We know in real life it's not feasible to have a road connecting to every 2 towns directly. So what we're going to look at is what's the cheapest way that I can connect all these places, knowing that I'm not going to be able to directly connect one town to every other town. So again, minimal spanning tree. I'm going to start with the edge of least weight. So that would be this 5 right here. That gets this town and this town. And then my next smallest edge would be this 7 right here. Again, it's not connected here, to this edge we've already selected, that's okay. Remember, we're not trying to make a path. We're just trying to make connections. Okay, so 5 plus 7. Now my next smallest edge would be this 8 right here. So those 3 towns are connected. My next smallest edge would be a 10. We've got 2 options here, this or this. Pick your favorite. I'm going to choose this one. Now my next smallest edge is this other 10, but if I include this 10, now I have a circuit in here. I form this little triangle, and we cannot have any circuits in our spanning tree, so I cannot pick this 10. If I had chosen this 10, my other option then at this point would be this 10 right here, and that would give me the same problem. So either way, no matter which of these I had picked, I'm only going to be able to select one of those 10s. My next smallest edge is 11, and I have 3 options for 11. This one I'm not going to pick because it will make a circuit. This one I'm not going to pick because it will make a circuit. And this one I'm not going to pick because it will make a circuit. So I'm not going to choose any of the 11s. They all make circuits. That's not an option for me. My next option, my next smallest edge would be 14. I've got 14, 15, and 17 left. 14 is the smallest of those. That does not make a circuit, and it does connect me to that last city. So 14 is the last edge that I will choose. That gives me a total of 44. This time we know our cost is in millions of dollars. $44 million to build this road system. And those are trees and spanning trees. Your homework is on the next page. Same types of ideas as what we looked at. So tell me if we have a tree or not. Give me a spanning tree, and then give me a minimal spanning tree.